Hello YouTube, good day to you, and we're gonna just pick up where we last left off. In the last video we just finished deriving du and ds, so you can find changes in internal energy and entropy. So now that we've done h, s and u, we can find g and a. Now how do we go about doing that? As a first easiest step, you can look at the definitions of G and A, and we find that if we have tabulated data of H and S or U and S, we can easily find the G and A at the state that we want to, right? So let's say you have state A, state B, you're going to find delta G. So the G1 here, or the G of A, equals to the enthalpy of A minus TA SA, right? Same thing goes for GB. Right? Otherwise, you can find like the delta H using integral of dH, and subsequently, you can find the entropy here as a reference and an entropy here from A to B. So if you know the entropy of A, you can actually integrate to get the entropy of B. So you get SB here and TB. So that's how we would find. Otherwise, tabulated data will be good. If not, you can use these integrals to help you find your dg, delta G, or delta A. For A is the same thing. It's just instead of H, you get U, right? So what if we don't have tables, right? What if no tables? Oh no, what are you gonna do? No tables. So let's just take a look at the equations we can actually use. We can try our approach earlier using the math method. Alright. Or we can look at this, which is something we used to derive our Maxwell relations. This comes from here. And this right? And what is this? So put this in here, you get your dH equals to right? So substitute this back in here, we get this. So this is a combination of a lot of equations already. So you can guess this is way like you have done lots of more work behind this, and this you will have to like start from scratch. So you probably don't want to do this, you want to do this. Because all the laws are incorporated. First law, second law, and the G and the H, the equations are all in there. So we can start with that. Right? So dg equals minus s dt plus v dp. Now, this is easy because if you have a PV graph or PV data, you can just plot and you do the integration. That's your VDP. The challenging thing is this. How do we do this? S dt, right? So from the looks of it, you probably have something like this, an S and T graph, and you get the area under the graph. That would be integral of S dt. Just get a minus sign and, you'll get this value. You can find your delta G. Now where are we going to get a graph of S and T? Now that's a challenging bit, isn't it? So you probably want tabulated data with T and S, like that. Now how do you plot a graph of T and S when there's so many ways you can change entropy, right? Well, one obvious thing you can probably do, right? If you just want to see how S changes with T, right? You can keep P constant. And you can ds at constant pressure equals to Cp over T dt, right? And of course you have some reference state plus your integral of Cp over T dt equals to S at whatever temperature, Tx. So it's from T of the reference state to Tx, you get this, T any temperature, right? So from this you can find, your T and S graph, and you keep pressure constant. So you can imagine like you plot many tables. Sorry, this should be S and T. So maybe you have a graph like this. I don't know how it look like. I'm just making up shapes. So equals this, maybe you can get like 1 atmosphere, 2 atmosphere, 3 atmosphere. I mean, you get the idea, right? So what you can do, you can just find the area under the graph of one of these, and then you can get your SDT value, right? Now, there's only one problem with that. You haven't accounted for the pressure change, right? You haven't accounted for pressure changes to find your delta G. So what do you do? What do you do when you have a system at like 300 K 1 atmosphere, you're changing to 800 K 10 atmosphere? What are you going to do to find your delta G? Well, the thing about delta G, or Gibbs free energy, it's a state function, right? State functions, they are the same. I mean, the change in state functions are the same regardless of what path you use. So you use a very easy path, or rather use a path that is easy to calculate. So let's say you first want to bring this to 800 K 1 ATM, then you increase the pressure here, right? An easy to calculate path is one where you don't consider pressure change, right? So dg is just minus SDT, right? And here, dg integral of VdP, right? So you have this part and you have this part. You can find your delta G. So the only T versus S graph you kind of need is the 1 atm graph. 1 atmosphere. Then you just find this PV graph, your problem is solved. And what if you don't start at 1 atmosphere? Let's say 500K, 5 atmosphere, 1000, 15 atmosphere. Oh, what are you gonna do? Alright. You lower the pressure to 1 atmosphere. Increase the temperature at 1000 at 1 atmosphere. And you integrate SDT here. Oh, wrong. Not SDT. Integral VDP. And integrate SDT right here. So you find delta G of this. You can find delta G of this, which is just VDP. Delta G here minus SDT, which you can use this graph. And delta G increasing from 1 atmosphere to 15 atmospheres at 1000 Kelvin VDP. So all in all, you sum all these up, get delta G. That's pretty much it, because you can do the same for dA. It's the same idea. Now dA equals to minus SDT minus P dV. So 500 Kelvin and V equals to V1, 1000 Kelvin, V equals to V2, right? So what do? You go to an easy reference volume. You change the temperature at that volume. And change the volume isothermally. And you can find your delta A. So here is your integral of PdV, integral of SDT, keeping volume constant. Right? So the only difference is when you do your calculation here, this is P equals constant, right? Constant pressure and constant volume. I mean, that's pretty much it, basically. So in summary, we can find our thermodynamic variables using data of this. So we have the equations now connecting these to these. These you can find from experiment. This is what you want to find. Right? Thanks for watching, guys. Hope you have a good day. See ya.